So, in our IG lesson today, we are going to be doing exam questions on patterns. And that is some on quadratics, majority is on quadratics. You might find some exponentials thrown in there, some linears thrown in there just for the fun of it, but we're going to be focusing on quadratics because that is generally the one that you guys struggle with. All right, so let me pull up the questions. Let me get to my folder. All right, so I'm going to pull up this one first. There you go, well done. I'll put it to this side. I'm then going to share my screen. Share. And which question is it? It is that question. All right. So here we have a nice, really simple looking little question. It just gives you a little bit of a pattern and it says, find the nth term of this pattern. Very nice and simple. So I need to get my pen. Now, remember, we have three patterns: linear, exponential, and quadratic. So if we had a look at this, we can take our first difference. Our first difference there is 6. It is then 10, it is 14, and it is 18. This, because this is not constant, means obviously it is not linear. So that we then check our second difference. If our second difference is not constant, it will then be an exponential. So our difference there is 4, 4, 4. Constant, meaning it's quadratic. And you remember that I gave you guys formulas for calculating a quadratic. So I told you that 2a equals my second difference, which is 4. I gave you a plus b plus c equals my first term, which is 5. And then I said there was another formula. 3a plus b equals my first difference. And I said you guys won't need this. And majority of the time, absolute majority, you will not need this. However, I have found one question in which you will need it. And that is why I'm adding this in so that you guys have it. So, here are the formulas, and we can now very simply start working this out. So 2a equals my second difference, so 2a equals 4, which means that a equals 2. Great. And you remember our general form, just in case you had forgotten, an squared plus bn plus c. So it's just like a normal quadratic or parabola where you have y and x's. The difference now is that your x's are now n's and your y is now a tn. Remember, n is your position and tn is your term's value. So we've got a is 2, 3a plus b equals my first difference. So 3 times 2 plus b equals my first difference of 6. So 6 plus b equals 6, meaning that b must be 0. Then we have a plus b plus c equals t1. So a is 2, b is 0, plus c equals my first term of 5. So 2 plus what gives me 5? C must be 3. So therefore, my quadratic is 2n squared plus 3. So let's check if that actually works. Because remember, checking can save your life. So if we sub in n as 1, we get 2 times 1 squared plus 3. 1 squared is 1, times 2 is 2 plus 3 is 5. That's great. We would expect nothing less because we've literally set it to be 5. If we have a look at the next one, we now let n be 2. 2 squared is 4. 4 times 2 is 8 plus 3 is 11. Looking good. We can try one more. 3 squared is 9. 9 times 2 is 18. Plus 3 is 21. We're looking all good, and we've got our 2 marks. This calculation, very simple. Then we go to our next one. Folder, there's my folder. The next one that I am going to do with you guys, yeah, that was quite a nice one actually. And then I'll go to that one. And I'll go to that one. Okay, cool. So the next one is we're going to be looking at some triangles. And I'm going to share again. I'm going to share that one. All right. So a question saying, how did we get the answer? I assume that was to the previous one, but that was the working out. So that was the 3 formulas that I gave to calculate A, calculate B, calculate C, and then you sub that into your Tn equation. That's how you end up with the final answer. So I wrote it just as 2n squared is actually Tn equals 2n squared plus 3. All right. All right, so very important question that came through actually. Why do we need to know that it's quadratic? Because I usually just use the formulas. Well, you need to know it's quadratic so you know to use the quadratic formulas. If it's a linear, there's no point in using quadratic formulas because they're not going to work. If it's exponential, there's no point in using quadratic formulas because it's not going to work. So you are essentially you're finding out what kind of pattern it is so you know what formulas to use. All right. Let's have a look at this problem. So we have got this shape, then that one, and it says each diagram is made from tiles in the shape of equilateral triangles, you can see at the bottom, and rhombuses. I don't know, I feel that might, to be more proper English, be rhombi, but I think that's kind of irrelevant for this question. The length of a side of each tile is 1 unit, which means that's 1 unit over there, that's 1, that's 1, that's 1, that's 1, that's 1, that's 1, that's 1. All right. And they say, there are your diagram numbers, the number of equilateral triangle-shaped tiles. So we can see that in this diagram there are 2, then there are 3, then there are 4. So you can see the pattern is you're just adding 1 every time. So you add 1, you add 1. Great. The number of rhombus-shaped tiles. Well, there's 1 here, there's 3 there, there's 6 here. So we're adding 2, we're then adding 3. So here again, you can see the pattern. We're going to add 4 to be 10. We're going to add 5 to be 15. So your total number of tiles, you could either just look at this pattern and say, okay, there to there, it's plus 3. There to there, it's plus 4. Cool, so I'm going to plus 5 here. I'm going to plus 6 here. So that's 21. Some of you may not be able to do that. But to get this row, luckily, all you do is you add. Because the total number of tiles is the triangles plus the rhombus tiles. 2 plus 1 gives 3. 3 plus 3 gives 6, 4 plus 6 gives 10, 5 plus 10 will give 15, and 6 plus 15 will give 21. And then we want to count the number of 1 unit lengths. So in this one, for example, we had 1, 2, 3, 4, 5, 6, 7, 8, as is there. This one is 15. This one is 24. We really don't want to have to keep drawing out diagrams. So here we see we add 7. Here we see we add 9. So we're going to add 11 to get 35. And we're going to add 13 then to get 48. So it then tells us the number of 1 unit lengths in the diagram follows this pattern. So Tn equals n squared plus 4n plus p. Notice we have a middle term. Now it says find the value of p. So p we need to replace with an actual numerical value. How are we going to do this? Well, there's a couple options, but most likely we can take the easiest one, which is taking the very first value and substituting it in. How did I know to do that? Well, think back to parabolas. Parabolas. If I gave you a graph with a point somewhere, and you knew that this formula was 2x squared plus x plus c, and I say to you, find the y-intercept, what are you going to do? You're going to take the other point, some other point on the graph, and you're going to sub in the y, you're going to sub in the x, and you're going to find c because it's going to be the last unknown. This idea is now applied exactly the same way here. The only difference is that we're dealing with a patterns question. But it's still quadratic, which means everything you know about quadratics still apply. So we just sub in 8 as my Tn, and my n value is going to be 1 because that's my term position. So 8 equals 1 squared plus 4 times 1 plus p. 1 squared is 1. 4 times 1 is 4. So 1 plus 4 is 5. 5 plus what gives 8? P must equal 3. Now, to save our lives, we need to make sure that we just quickly check this. So we know these values. So let's sub in for 3. So I have T3, and T3 is actually going to be 24, should equal 3 squared plus 4 times 3 plus 3. So 3 squared is 9, 4 by 3 is 12, so 9 plus 12 is 21, plus 3 is 24. Indeed, this formula does give me the 24 that I'm looking for. And you can test any of the other ones as well if you want, but we can see that P does equal 3. All right. Then they say to you, calculate the number of 1 unit lengths in diagram 10. So you have your formula for 1 unit lengths. So diagram 10, this is giving me my n value. So I'm looking for what is T10. So it's going to be 10 squared plus 4 times 10 plus 3. 10 squared is 100. 4 by 10 is 40. Plus the 3 makes 143. And there we go. Simple. So this question initially looks really complicated, but the skills required to actually do it is far less cumbersome than what it initially looks like. Question on that? All right. I am going to bring up my next one. This one should be quick, and then we hopefully should be able to get. All right. So the question says, how did you find n? I assume that n is for the last one. So my n value is from my diagram number. So these diagram values here, that represents my n value because they link to my term number, which is what n actually stands for. So my first term, my second term, my third term, my first diagram, my second diagram, my third diagram. All right. And where is my next question? My next question is this one. Great. Mouse. I'm going to stop this share and then I'm going to share the next one, which is that one. Good. All right. Get my chat back. Good. So this one says we've got diagram 1, 2, 3, 4, and blank 5. Diagram 1 shows 2 lines of length 1 again. And they are at right angles forming an L shape. 2 L's are added to diagram 1 to make diagram 2. There you go. There's an L and there's an L. This one forms one small square in the middle. 3 L's are added to diagram 2. One over there, one over there, one over there. To make diagram 3, you now have 3 small squares. And the diagrams continue. We need to draw diagram 5. Well, we've got 1, 2, 3, 4 lines at the bottom, 1, 2, 3, 4 lines at the top, diagram 4, 3 lines, diagram 3, 2 lines, diagram 2. So it makes sense. There's going to be 5 lines at the bottom and 5 lines at the top. Now you may see I'm not drawing the L shapes, and that's because I am choosing how I'm going to draw this. The marker has no idea how I've decided that I'm going to do this. If I've drawn the L's, kept drawing the L's, or if I can see an easier way. And I most definitely can see an easier way because I'm just going to fill up the squares because that is what the shape does. And there's your shape. You can see there are all my L's on the top. There you go. Very nice. Get your marks, and no one is any the wiser. So we have over here, we are asked to complete the table. The number of lines of length unit 1. So diagram 1, there are 2 lines. Diagram 2, there are 6 lines. Diagram 3, there are 12, 20. Diagram 5, we can look, we can totally count, or we can follow the pattern. So just in case you have somehow messed up this diagram, it's a good idea to rather use the pattern to get this value instead of counting. And then if you use the pattern, you can then count to see if this diagram links or not. And that's a nice way of checking if that diagram is actually correct. So here we see that we are adding 4, we are adding 6, we are adding 8. You can see the pattern clearly now. So we're going to add 10. 20 plus 10 gives me 30. And the number of small squares, well, we'll add 1, we add 2, we add 3. Very clear for us to see what we're going to do. So we add 4, and we get 10. So let's count our squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Looking good. All right. Find an expression in terms of n for the number of lines of length of unit 1 in diagram n. So we are going to take this pattern, 2, 6, 12, 20, and 30. we need to check what kind of pattern it is so we know what formulas to use. So the difference is 4, difference is 6, difference is 8, and difference is 10. Not a linear. So we go again. Difference is 2, difference is 2, difference is 2. It is constant, therefore it is quadratic. So we have our formulas. 2a equals my second difference. My second difference is there. 2a equals 2. A is 1. Great. So Tn equals 1n squared. I then have 3a plus b equals my first difference, which is 4. My a value is 1. So 3 times 1 plus b equals 4. 3 plus what gives 4? Well, 1. So notice here we actually have a middle term, 1n. And then I'm going to go all the way up to the top because I have space. A plus b plus c equals my first term, which is that one. A is 1, b is 1. First term is 2. 2 plus what gives 2? Nothing, which means that is my formula. Very mechanical, very repetitive. It's you just do the work, do the work, do the work, and the answer falls out. Let's just check this works. So if you sub in 1 here. You sub in n as 1 because it's diagram 1. You should get an answer of 2. 1 squared is 1, times 1 is 1, plus 1 is 2. Great. But diagram 1 we know should work anyway. Diagram 2, sub in 2. 2 squared is 4, plus 2 is 6. Good. Diagram 3. 3 squared is 9, plus 3 is 12. Good. Last one, diagram 4. 4 squared is 16, plus 4 is 20. So that looks very good. Lastly, they ask you, find an expression in terms of n for the number of small squares. So that's this one here. So we've got 0, 1, 3, 6, 10. Once again, you do the exact same thing. We can see that this is going to be quadratic again. So we take our differences. It was 1, 2, 3, 4. Now differences after there are all 1s. So we can have a formula. 2a equals my second difference of 1. A is a half. 3a, which is a half, plus b equals my first difference of 1. So 1.5 plus something gives 1. That is minus a half. And then to calculate c, it's a, and a is a half, plus b, which is minus a half, plus c equals 0. Well, that is 0. That is 0. Everything is 0. You get a 0. You get a 0. Everyone gets a 0. So therefore, my Tn is a half n squared minus a half n. And once again, we check to make sure. So we sub in 1. 1 times a half is a half, minus a half is 0. Diagram 1 we expect to work. Diagram 2. 2 squared is 4. Half of 4 is 2. And 2 times a half is 1. So that is 2 minus 1 gives 1. We can check one more with 3. So 3 squared is 9. 9 over 2 is 4.5. Time 4.5 minus 1.5 gives me 3, which means that is correct. All right. So, very interesting questions. I hope you guys see that a lot of this quadratic work is actually very repetitive. You do the same process, you find your differences, you come up with your Tn, you sub a value in, that's all that you do. All right. I have one other one that I was going to do, but I'll keep that for next time. And then we're going to move on to a new section.